All right, so today we're going to go a little out of order. That snow day on Thursday kind of messed things up a little bit, but oh well. So did the pandemic. So what we're going to do is that I'm going to skip 8.3, which is finding our known proportion. So we know the population standard deviation. Then we know the sample standard deviation. 8.3 was going to be what if we have a sample proportion. So when we come back from break, we're going to revisit the sample size thing and we'll resume with proportions before we move on to chapter 9. So I'm now going to move on to the last section of the textbook in chapter 8. Actually, nope, I think that's a lie. Yeah, we got more in chapter 8. Anyway, we're going to move on to section 4 in the textbook. It was actually part of section 1 in the PDF. So I made the mistake for some people. There was an extra question in one of the problems that said find the sample size, and I had overlooked that because the textbook, which is what I'm following, doesn't do that until section 4. So I apologize for the confusion. For those that got it wrong, I just kind of skipped it. Those that got it right, nice job. So this section is choosing the correct sample size. So what we have here is the formula for finding the correct sample size. We have n equals, and then the z sub c, again, is our deviation that corresponds with our level of confidence. Our sigma is going to be our standard deviation. So that can either be sigma or it can be s, depending on the information that we have at hand. E will be our allowable margin of error. So we get to decide, well, not you, but in general, the process would be you would decide how much error you're willing to have in your estimate, and then what sample size would be needed in order to obtain an X bar value that would be within that margin of error of our population mean. Now, keep in mind, the more samples we take, the closer we'll be to the population mean. Because if we take enough samples, that might become the new population because it's been such an insurmountable number that it's big enough to say that this is now our population mean. So if you were to do something 1,000,000 times, maybe in your lifetime you've done it 1,000,000 and 1,000 times. So that million is going to bring you closer and closer to your known mean, the law of large numbers. And then after you find that quotient, make sure you remember to square it. That's going to be pretty essential. So just to dive right into it, I have this example. We have a wildlife study designed to find the mean weight of all salmon caught by an Alaskan fishing company. As a preliminary study, a random sample of 50 freshly caught salmon is weighed. The sample standard deviation of the weights of these 50 fish is S equals 2.15 pounds. How large of a sample should be taken to be 99% confident that the sample mean, X bar, is within 0.2 of a pound of the true mean weight, being our population mean? So I'm going to write down the information that I know. My z-score is a z-score referring to the 99%, so that's 2.58. We can find this value from the table, also using the inverse norm. That would do it as well. The sample standard deviation is 2.15, and our margin of error was 0.2. So I plug in each value. I'm going to multiply these two first, then divide, then square, and I get approximately 769.2. So the answer to this question would be, in order to satisfy the expectations of the study, we would need a sample size of 770 salmon to be within 99% sure that the mean weight, X bar, is within 0.2 of a pound of the known mean. So if we were to collect 770 salmon, that sample size would be large enough for us to be confident that we would be within that margin of error. So your homework is to use your 100 trials. So we're going to figure out your sample size of your 100 trial experiment. If you wish to be 95% sure you are within 10% of your current X bar. Now, everyone has collected different information, so that's why I had to use 10%. I'm not going to give you a set margin of error because everyone would have their own applicable margin of error. I figured this blanketed question would be sufficient for everyone. And so I'll show you the mathematical expectations of the 10%. So if you rolled a 3 on a standard die, on average 1.2 times every 5 throws. So this was the thing that I did 100 times. I threw a die and I was looking to get a 3. I threw it 5 times. How many times out of those 5 did I get a 3? Well, 1.2 times out of those 5 throws, a 3 came up. So how many times would I have needed to throw the die 5 times to be 95% sure I am within 10% of my X bar when my standard deviation is S equals 0.7? So the 95% confidence is 1.96. We will all be using this value. My sample standard deviation was 7/10. So that will be different according to your value. And so my margin of error is what is 10% of 1.2? So 10% of 1.2 gave me 0.12. So my specific margin of error would be 12 hundredths. So I plugged in this value, which everyone's gonna be using the same number. I plugged in my standard deviation and my mean, squared the quotient, and I got about 130.7. So that means I would need to roll my die 131 sets of 5 throws to be 95% sure my mean number of times, X bar, is within 10% of my population mean, mu. So your homework is one problem. It's taking a look at your values and figuring out how big of a sample size would you have needed to have to be 95% sure. Now, when we come back from break, we are going to revisit the confidence intervals, because you are also going to be calculating a confidence interval of your sample information, but we're not going to do that until we get back. So just focus on the desired sample size, one question for today, and we will go from there. So good luck. If you need any help, please feel free to come into Zoom.